Finally, we will introduce the powerful bound called Chebyshev's inequality. This bound is stated as follows. Suppose that x is a random variable. Notice that there is no restriction on x, so x can be any random variable. Then, for any positive value a, the probability that x minus ex, so the difference between x and ex, is more than or equal to a, will be bounded by the variance of x divided by a squared. So as a goes larger and larger, the right-hand side will be smaller and smaller. So we have established a bound on how x deviates from ex a lot. So graphically, it is something like this. Suppose that this is the rectangles here are depicting the probability distribution of the random variable x. And let's say this line, this brown line here, represents the value of expected of x. So expected of x has a value here. So we are interested in the total probability of the area outside the range of a away from expected of x. So if you can see, the green box corresponds to the cases where x is deviating from ex by at least a. The Chebyshev's inequality says that the total area of this green part cannot be very large. It is always smaller than or equal to the variance of x divided by a squared. Okay, so how can we prove this result? Actually, the proof is very interesting. We just need to apply Markov inequality, and then we can show the Chebyshev's inequality is correct. So let's see. So this is the left-hand side of the Chebyshev's inequality. The probability of x minus ex is greater than or equal to a. So we have an absolute value here. Now, when we say the absolute value of something is greater than or equal to a, it means that the square of this value is greater than or equal to a squared. So these two things are equivalent. So we have this is equal to the probability that the square of x minus ex is greater than or equal to a squared. Now, if you look at this one, this is a random variable as well. And this random variable can only take on non-negative values. So this is the condition that allows us to apply Markov inequality. So by Markov inequality, we will see that this probability is bounded by the expected value of this big random variable, x minus ex whole square, and divided by this term. This term is a squared. But expected of the value x minus ex whole square is exactly the definition of variance of x. So this is the same as the variance of x. So now we get the Chebyshev's inequality shown. And then we can have two very related corollaries, but they are just a direct plug-in result from the previous theorem. So here, we say that for any positive value r, the chance that x minus ex is far away from r times standard deviation of x cannot be a lot. This probability is less than or equal to 1 over r squared. We just recall that sigma of x, this standard deviation of x, is simply the square root of the variance. So r times sigma of x is equal to r squared times variance of x. So we get this one. And for the last part, here we change this term to r times expected of x instead. So by plugging it as the a value in the original formula, we get this corollary. So we have talked about Markov inequality and also the Chebyshev's inequality. And when we apply the Chebyshev's inequality, then a good thing here is x can take on negative values. So there's now no restriction about whether x has to be non-negative or negative. And then But then when we apply this one, it needs both the value of expected of x and the variance of x ready. And usually, this Chebyshev inequality will give better bound than the Markov inequality. It is because for Markov, we just need this expected value of x, but for this Chebyshev inequality, we get both ex and variance of x into consideration. So it is based on more information. So naturally, it gives us some better bound. So let us see two examples here. So the first one is, let us say we are going to flip a fair coin n times, and we let x to be the number of heads. So based on this, we can immediately compute expected of x is equal to n over 2, and the variance of x is equal to n over 4. So n times p times 1 minus p. So npq, so n over 4. And let us try to bound the probability of x greater than or equal to 3n over 4. Now, for Markov is just less than or equal. So this one x is always taking on non-negative values. So that's okay to apply Markov. So for Markov, it is less than or equal to expected of x divided by 3n over 4. So after simplification, this is 2 over 3. And for Chebyshev's inequality, then we first change this to the correct form to apply. So instead of having x on the left-hand side, we change it to x minus e of x. And x is 3n over 4. So x minus e of x here will be like greater than or equal to n over 4. And then, so here it is not equal. The reason is that we are taking absolute value here. So the absolute value caters for both cases where x minus ex is greater than or equal to n over 4, or x minus ex is less than or equal to minus of n over 4, something like this. So we have this smaller than or equal to sign here. And next, this is the Chebyshev's inequalities result. So this is less than or equal to the variance of x divided by the square of this part. Now, because the variance of x is n over 4, when we divide it by n over 4 square, we will have 4 over n as a result. Now, if you compare these two things, they are talking about the same probability thing. They are working on the same bound for this probability, for this case. And so, both of them are correct. And then we will see that 4 over n is a more accurate result than 2 over 3. Yeah, because here we want to show that this is actually very small, and this time is smaller than this one, so this is actually a tighter bound. So this is an example that Chebyshev's works better than Markov. Let us also revisit the coupon collector's problem we have studied before. So consider the problem with n cars, n distinct cars, and we let x to denote the number of draws that we need to get a full collection. Now previously, we have shown expected of x is equal to n times the harmonic number of n. And the variance of x we have not computed yet, so let's leave it blank here. And for this example, we want to bound the probability that x is greater than or equal to 2nhn, 2 copies, or two times of the expected value. So what is this bound? So by Markov, it is easy. So by Markov, it is less than or equal to expected of x divided by this term, so it is 1 over 2. But for Chebyshev's inequality, then we will need to find variance of x first before we can get any conclusion. Okay, so what is variance of x? Now recall that x represents the total number of draws to get a full collection. And previously, we have tried to simplify the analysis by defining or by separating this collection phase into subphases, so that each or stages, so that xk only focus on the number of draws that are needed at stage k, where stage k is, where stage 1 is the number of cards that where stage 1 is the case where we obtain the first card. Stage 2 is after stage 1, the number of cards that we need to draw in order to get the second unseen card, and so on and so forth. So this is the xk that we have defined before, and then recall that this xk, every one of them is a geometric random variable, and the parameter is known, so to be something like this. And all these xk's are independent of each other. Now, because of the independency, so we will have linearity of variance. So the variance of x is equal to the variance of x1 plus the variance of x2 plus the variance of x3, and so on and so forth. And recall that for geometric random variable, the variance is less than or equal to 1 over p squared. So in that sense, we can simplify this variance of x into a bound of less than or equal to n squared over n squared plus n squared over n minus 1 squared, and so on and so forth, up to n squared over 1 squared. And by doing some trick to bound this one, this is always less than or equal to 2n squared. The bound is actually not difficult to see, so I will leave this as an exercise for you. And now we can proceed to find out what is the bound for this Chebyshev inequality. So the probability of x greater than or equal to 2n times h of n will be less than or equal to, so we change this into the form that we can apply Chebyshev's inequality, so x minus ex absolute value. And here, this is greater than or equal to n times h of n. Again, this is smaller than or equal to sign because we are taking absolute value, which has two cases. Okay. And then, so we have something like this. So now, this is the important term that we have. This is the a term when we apply the Chebyshev's inequality. So this one is less than or equal to the variance of x divided by the square of this part, so nhn squared. And so what is it? So variance of x, it turns out that it is less than or equal to 2n squared. So it is like order of n squared here. The bottom part is order of n squared log n squared. So after doing cancellation terms, we find that this is of the order of 1 over log n squared. And notice that this is a much better bound than 1 over 2 as n becomes large. Because when n, let's say n is equal to 1000, then this is only 1 over 2, but this is 1 over 100. When we are talking about the same thing, this gives us a tighter bound. Okay, so this is the end of the second example.